All right, now that we understand a little bit about electric flux, and if you need to review electric flux, go back and check out that video, we can look at Gauss's law and how we can use Gauss's law to look at what the electric field might be in a given area. So let's just kind of remind ourselves what we mean by electric flux. Remember we said that the electric flux is equal to the electric field, oops, not the D, and the dot product between the electric field and the area. So the electric field through a certain area. And if we have a planar area, it's just the electric field times, with the dot product to that area. So we might have to look at the angle between the electric field and that area. Again, check out that video. If it is an uneven surface, we take the integral across that area and we get, of course, the integral of the electric field with respect to that area, and that gives us the flux. Now, if I take that area and I enclose a full space, so instead of just the surface, this kind of irregular surface that the electric field is going through it, that surface is enclosing a space, a volume, then I take the integral across that entire surface, so around the surface, and we write that with that kind of integral sign and a circle around it. So I'm taking the integral over the entire surface of that enclosed volume. And what might that look like? Now, let's just give a specific, this again equals our flux. Let's give that a specific example just to solidify this, because it's this that leads to Gauss's law. So let's imagine that that enclosed surface is a sphere. So you imagine that you have a sphere, okay? And that sphere is immersed in an electric field. Okay, so that sphere is immersed in an electric field. So if I want to look at the flux through that sphere, I'm going to take the integral across the entire sphere to get at that flux. All right, now what do we notice? Flux. What do we notice about the field lines entering that sphere and the field lines leaving that sphere? Well, everything that comes in goes out. So the net flux through that area, everything that comes in goes out. The net flux through this area is equal to 0. So there is no net flux through that surface. So how would I get a net flux with an enclosed surface? The only way to do that is if that enclosed surface is enclosing a charge. So imagine, again, that we have this sphere, and inside this sphere, and instead of it being immersed in an electric field, I have a charged particle in that electric field. We know that the electric field lines have a positive charge point out. Check out the electric field video if you kind of get a reminder of how electric field lines work. The electric field lines point out, and now I have a flux through this surface. So I do have a flux of an enclosed charge. All right? So we have the flux of an enclosed charge. So let's look at that. Similarly, we might imagine that if I had a negative charge here, if it was enclosing a negative charge, well, then the field lines are all pointing in, and again, there's a flux through that surface. So Gauss's law tells us that in order for us to have a flux through a surface, that the charge that encloses a space, surface that encloses a space, that the charge must be enclosed. This gives rise to Gauss's law, and we're going to just write Gauss's law. What do we think the amount of flux is dependent on? So again, this is our flux equation. So we have the flux, which is the integral along the surface of the electric field over that volume, over that surface area. And it's dependent on how much charge is enclosed Okay, so if I increase the amount of charge enclosed, well, if we think about a point charge, I increase the electric field exerted on that by that point charge, and then I would increase the flux. So that makes some sense. That's proportional to the charge enclosed. It's also inversely proportional to this epsilon, which we introduced this epsilon in our Introduction to Coulomb's law. So this again is the same permittivity of free space. So go back and check that lecture out. This equation here is what gives rise to Gauss's law. So this is Gauss's law. Again, Gauss's law tells us that the flux is equal to the integral across that enclosed space of the electric field across that surface area. It's equal to the enclosed charge, the charge enclosed in that space that we're taking the integral over, divided by the permittivity of free space, so epsilon naught. Right, that's Gauss's law. Now, how do we use it? And how have we actually experienced it already? So we're going to start with the latter. How have we kind of experienced it already? How can we connect it to something we already know? And then in the next video, we'll do an example of how we could use Gauss's law to determine the electric field in certain regions of space based on how charges are existing in that space. So first, where did we actually see this, or how can we connect it to stuff we've seen in the past? I'm going to erase this. I'm going to imagine a point charge. So let's imagine that I have a positive point charge, positive Q. And I'm going to draw an imaginary shape, a Gaussian surface, we call that, an imaginary shape around it, to look at what is the electric field of this point charge. Now, the easiest mathematical shape to draw that is going to be uniform in this situation is a sphere. Okay? So imagine a sphere around this point charge, Q. Now let's look at our flux equation. For a given positive charge, we know that electric field is radial outward. So this, as I integrate the electric field across that surface, what's changing isn't the electric field, but the surface area, so are the little pieces of the surface area. And the integral of the surface area over a sphere is simply the surface area of a sphere, which is 4 pi r squared. So my flux through this, for this point charge, is the electric field, which is not dependent on the area, because it's a uniform sphere, times the surface area of that sphere. Okay. Gauss's law says that this, so this is the flux, Gauss's law says that the flux is equal to Q enclosed over epsilon naught. Boop. So E times 4 pi r squared is equal to my Q enclosed over epsilon naught. So in a little bit of rearranging, I'm going to pull 4 pi r squared over on this side. So my electric field is equal to Q enclosed over epsilon naught times 1 over 4 pi r squared. Now I'm going to do a little rearranging. No mathematical specialty here, just moving things around appropriately. And I end up with 1 over 4 pi epsilon naught times Q enclosed over r squared. So I just took this 4 pi, I put it here, I moved Q enclosed over there, really just rearranging of some variables appropriately. But what do I notice? This, well, that's Coulomb's constant. So I end up with the electric field equaling K times Q enclosed over r squared, which is KQ over r squared. This is Coulomb's law that we learned about in electric field form. So our idea of Gauss's law really is a way that we describe what the electric field looks like in a space. And I'm glad it's consistent with what we already know in terms of Coulomb's law. So how do we use this? We're going to look at an example of using Gauss's law to determine the electric field in a space, as well as how we can think about looking at electric field through space given the charge distribution that exists in a space. We're going to do pretty straightforward examples. I'll give you one practice or an example problem in the next video, and we'll be having fun exploring Gauss's law. All right, good job.